My talk today is dedicated to Han-Dong Gui. He was a PhD student in electrical engineering, got his PhD in May 2020, and then just tragically passed away a couple of months later of a heart attack. He was an excellent student and an even better person. The energy consumption in the United States, as you can see presently, is more than 80% fossil fuels, petroleum, natural gas, and coal, and less than 20% is nuclear and renewables. That percentage, of course, is going to increase. Our global energy consumption is expected to increase more than 50% over the next 30 years. There will be some growth in the developed countries, shown in the dark blue, but most of the growth is going to come in developing countries over the next 30 years, and most of that in Asia. Our U.S. transportation electrification is occurring as we get more electric vehicles, and that's going to increase significantly over the next 30 years also. But as you can see, in the next 30 years, it's still not going to be the major component of how we power our vehicles. We'll still be using gasoline and propane and other things. Our global energy consumption, though, is going to transition to renewables in the next 30 years. You can see a huge increase where renewables will make up the majority of our power in 2050, but all of the others are also increasing, coal, natural gas, petroleum too. So where's our CO2 reductions going to come from? It's going to come from reducing how much we use and being more efficient in how we use it. So cars with better gas mileage, more efficient lighting, motor drives, and then there will be some reduction due to renewables and nuclear. The key renewables that we're going to count on as we transition is going to be, of course, solar and wind, but one that some people forget about is biofuels. And then some other renewable energy resources that are going to make up some of our future energy are geothermal, tidal, and wave energy. But energy storage is the key for renewables because there's a lot of variation in our generation, and so we're going to need a way to store it when there's a lot of renewable generation and then use it when there's not as much, when the wind stops, or at night when there is no solar. And as we can see, our best wind and solar resources are in the Great Plains or in the desert Southwest, but not many people live there. Of course, most of the people live in the eastern U.S. or along the Pacific coast, and so our electric grid needs to be changed to move power from this. And so at the University of Tennessee, we have an engineering research center established by NSF and DOE called CURENT, where we are looking at high penetration of renewables and how can we move this power to where it's needed. CURENT also has a large education program. We're working on K through 12, doing things like science fair and parents' night, working with teachers to provide research experiences for them and high school students, leading to undergraduates where we're also encouraging them to pursue research as a grad student. We also have a lot of industry members in CURENT. We have more than 35 traditional utilities like TVA and KUB. We're also working with a lot of vendors, and we have 5 national labs and several industry consortia that are CURENT industry members. We also have a lot of nice facilities at CURENT. We have a high power lab where we can do testing of power electronics, as well as a low and medium power lab. And then we have a grid emulation lab, as well as a visualization and control lab that's part of the CURENT facilities. One of the things that we also have in CURENT is the ability to monitor the frequency nationally and bring that data. This shows how an outage in Florida actually affects the entire eastern interconnect or the entire eastern grid. And at CURENT, we're working on ways to reduce the impact of these outages and try to mitigate how they affect the entire grid. We've developed a hardware test bed where we can emulate the entire North American grid, which consists of an eastern grid, a western grid, and Texas. And we've connected that with a high voltage DC so that we can accommodate a high penetration of renewables and be able to move power from one region to another. Our visualization wall allows us to control power, to control generation, look at things like outages, short circuit, change in wind patterns, change in solar, and just monitor frequency, voltages, and currents and be able to see how well that does. We're also able to look at smaller things like microgrids and integrate community solar. Here we're showing increase in solar and how it can power more load as we have more solar available, and be able to just look at how could this impact our energy usage at a local scale. We also work quite a bit on power electronics and current, looking at things like high efficiency power electronics used in things like data center power supply, used in electric vehicles, more electric aircraft, also looking at interface with renewable energy, as well as consumer electronics and medical devices. So how are we going to reduce global warming and reduce our CO2? It's going to really take demand-side efficiency improvements. As we've seen, it's not just going to come from having more renewable generation, but really from using less energy. And so if you're wondering, well, what could I do to help? Main thing is just use less, because if you use less, that means we can generate less. And that leads to, of course, less drilling, less mining, less transportation needs, and just less energy in general that's needed.